Greetings and welcome. In today's lesson we're going to be looking at polynomial functions, and we're specifically going to be looking at polynomial functions of a single variable. So when I say that, I'm referring to a function like f of x equals 2x squared plus x minus 1, for instance. So we're used to polynomial functions like this. This is specifically a quadratic function, all right, because of its second degree. But we're going to branch out. Instead of just looking at quadratics or linear functions like we've done in the past, we're actually going to expand it. So what if I have a polynomial function? I could have one that says negative x to the fourth plus x squared minus 5x plus 7. All right, so here's a quartic polynomial function. And when I say of a single variable, I'm referring to the fact that all of these are defined in terms of just a single variable taking place here, right? All of these are in terms of x. And I'm also allowed to have a constant term as well. And also one of the limitations of a single variable, I wouldn't be allowed to have, say, a negative exponent, for instance, or some sort of like a square root term or anything like that. All of the exponents have to be integer exponents in some degree. And also when I say of a single variable, I'm not allowed to have like an x squared y term or something like that. So the first thing that we're going to do with polynomial functions is learn how to evaluate them. Just get used to this concept of this notation, f of x or p of x or h of x, whatever it may be. And this is really equivalent to my output. It's another representation or name. I technically could have represented this as y equals this whole expression, and that would be fine. So this is kind of like my y value. If I was to graph it, it would be represented on the y-axis. So it's my output. But the thing that's beneficial for this notation is it allows us to calculate represent what the input and the output is at the same time, without using like an ordered pair or something like that. So suppose I wanted to calculate what f of 2 was. So we've done this before. So f of 2 would be 2, and what this means is I'm replacing the x. Every x in the function is now going to be replaced with a 2, right? Substitution, essentially. So I would just go through and replace all of those with 2's and evaluate using order of operations PEMDAS. So 2 squared is 4, plus 2 minus 1. 2 times 4 is 8, plus 2 minus 1. Scrolling down, let's see. So, and then I'd get 10 minus 1 or 9. So I find out that f of 2 equals 9. Now if I wanted to represent this as an ordered pair, this is the same as if I wrote it as when the input's 2, the output is 9. Or graphically, that would be the same as if I'd represented it as a point that is over 2 up 9, right? So the point 2 comma 9. So 1, 2, and then let's say I counted up to 9. Let's say that was up to 9. Something like that, right? So graphically, here it is in this function notation, f of 2. I also could have said y equals 2 when y equals 9 when x was 2, right? I represented it as an ordered pair or a graph. So that's kind of the relationship between all of those things. It gets a little bit more complicated. I can evaluate things more than just numbers. I technically could even evaluate a variable. Let's try a negative number. And actually, let's work with our other function. What was that? So let's calculate p of negative 3, for instance. So what I'm going to do, everywhere there was an x up here, I will now plug in a negative 3. So I will have negative of negative 3 to the fourth plus negative 3 squared, and minus 5 times negative 3 plus 7. Right, and now all I have to do is evaluate this, so we can go through and do that. So negative 3 to the fourth, well, 3 times 3 is, negative 3 times negative 3 is positive 9, and 9 times 9 is 81, so this is going to be negative 81. So this sign became positive because being raised to an even exponent, but this minus sign was unaffected by it, so that's why it's still negative on the outside. Plus negative 3 squared is positive 9. Negative 5 times negative 3 is positive 15. And plus 7, right? And now I can just go through and simplify. So negative 81 plus 9 is negative 72. Let's see how well I can do my math here. And negative 72 plus 15, so that's the same as 72 minus 15, taking the sign of the more influential. So 72 minus 10 would be 62, minus 5 is what, 57? And negative 57 plus 7, once again I'm taking the difference, and then the sign of the more influential. 57 minus 7 is 50. So I find out that p of negative 3 is equal to 50. And if I wanted to represent that as an ordered pair, like I said, that's the same as if I wrote negative 3 comma negative 50. Or the output is negative 50 when the input was negative 3, when I plugged in negative 3, right? So that's kind of an interesting thing I could do as well. Let's see. And let's do another example. You can also plug in an expression or a variable. So let's plug in, let's calculate what was f of, let's say, x plus 2. So this time I'm plugging in a whole expression, x plus 2, everywhere I had an x in the original problem. Let's see, let me copy and paste this. So if this is my original function, and I want to calculate f of x plus 2, that means everywhere there's an x, I'm going to substitute x plus 2 in parentheses. So f of x plus 2 is equal to 2 parentheses x plus 2 squared plus x plus 2 minus 1. This set of parentheses isn't as required. So here I can't distribute yet. Also I can't distribute an exponent over addition. That would be illegal. But I can use a pattern. So I'm going to use this square of a binomial pattern. It's going to be x squared plus 4x plus 4. And then plus x plus 2, dropping those parentheses, minus 1. And now I could distribute the negative 2 to all of these terms and just simplify what I can. So I'll get 2x squared plus 8x plus 8 plus x plus 2 minus 1. And then I'll go through and combine what I can. So for the x squareds, I don't have any other x squared terms, but I will be able to combine the 8x with the x, and I'll combine the 8, the 2, and the negative 1. So let's see, it looks like I'll get 2x squared. For my linear terms, 8x and x is a total of 9 x's, and then 8 plus 2 is 10 minus 1 is a positive 9. So this is the function f of x plus 2. Right? So when I plugged in x plus 2, this is what I got back. So using this function notation, which we've used before, but I don't think we've plugged in expressions into them before. So this is kind of the first thing that we can do with polynomial functions. I just want to point out that linear functions and quadratic functions, the one we're used to, are technically types of polynomial functions. We've dealt with those before, but we also can expand to cubics and fifth degrees and 10th degree functions. And we're actually going to try to analyze those in the next video. Alright, so thanks for watching. I'll see you in the next vid.